Hola a todos and welcome to another Julia video. In today's video, I want to talk to you about something that probably already happened to you. Your code is working, but it's slow. How do you figure that out? You probably have already timed your code, but then when you have to actually go through every part of your code and breaking down to see what specific part is slow, you're gonna have a bad time. Julia has a few tools to help you figure out where the problem lies. For instance, benchmark tools and chair marks to help figure out what's really slow, or you can use code warn type or JET and other type stability tools, and even profiling with the profile and prof view tools that are available via VS Code or via the terminal. And today I want to talk to you about a new tool that's being released recently. It's a tool called CodeGlass. It allows you to profile your code with little intervention. So you can do your normal use of your package, your normal use of your code, and you can just see what's happening in real time. So CodeGlass is a tool that traces your Julia application, essentially looking at every call, every allocation that you make, and then it provides you with a few views that help you figure out where the problem lies. CodeGlass is a proprietary tool, so we are using a demo version, a trial version. You can also just download the trial yourself and try in your code. But before we do that, I want to show you a few examples of debugging profiling with CodeGlass. Maybe you'll find that interesting and help determine if you want to go try yourself. But let's go into the details. Okay, so I have already started the application. If you don't know how to do that, download the trial, install, unpack, whatever, run it, and you have a login page, and after the login page, this is the main view of the application. You can add a new application here. So Julia repo or a project, we're just gonna open a repo here. I'm going to use my YouTube showcase name, and you can select whether you want just the regular Julia experience or some pre-computed filters, or even remove the inlining so you can see everything that's going on. We will use the filters that are pre-computed, so something like core or the Git stuff that's not gonna show in our profile. That's useful. Okay, this is inside the YouTube Showcase application. The settings can give you some useful information. So one of the useful things for me is to add this startup file equals no, because I do have a large startup file, and also setting up which terminal I'm using, which is Vesterm-E, which I got from this help in the docs. So if you don't know exactly what to put there, just go in the docs and figure it out. Okay, let's start the application. Okay, so you can see that the terminal is running Julia. So this is the CodeGlass Julia. I'm gonna move this to the side a little bit. We'll just start on the main view, clicking on statistics, and you can see some things are already happening. This is just basic Julia. Just by starting Julia, you already have something going on. You can ignore that part. And I will, for this test, only use the terminal. So the first example that I prepare, maybe you're gonna find this kind of obvious because you already know Julia a lot. Try to see if you can figure out the issue before I can figure it out using CodeGlass. Of course, I already know the issue, but see if you know enough about Julia to say what is the issue before I use CodeGlass to investigate. Okay, so this is the first example that we are looking at. We are normalizing some data input. So far, nothing has been called. Of course, everything that I use here has resulted in something changing here, but don't worry. Let's say that in my application, I have this normalize function. And when I call normalize data, I see, oh, this is slow or it's creating too much memory. Why is this an issue? Okay. So first of all, let's just browse the views and see what they show. This is the first view, the statistics view. It's showing a lot of statistics for the CPU runtime. So I have a function normalize. The input of the function was inferred correctly. The output was inferred correctly. It was called once. The exclusive call type, so only the function itself took 483 milliseconds. Inclusive call is like the function, and the things that the function called took 887 milliseconds. So most of the function time is spent on the function itself, not on internal things. And of course, we don't have other functions being called, so that makes sense. You can see other useful information, and you can also see the allocation here. It's all in kilobytes, so let's improve the visibility by changing to megabytes. 36 megabytes have been exclusively allocated. Inclusively, we have the same, 36 megabytes. So, does that make sense or not? We have 2000 allocation. We have in our function normalize, let's go back to the code, similar call. So this result equals similar. It's creating an empty vector of the same format as data, so that we will allocate 1,000,000 float 32s. Then I will assign this division of data I by scale to the result. Maybe I create an intermediary value here and save it in result, and because of that I have 2,000,000 allocations. That's possibly why we have 2,000,000 allocations. One view that I like a lot, especially when dealing with the super heavy stuff, is this performance view. And you can see the profile functions, allocated objects, all the stuff that's happening here. Another interesting view is the memory profile, the memory statistics. So you can see here pretty much the same as the normal statistics, just the ones that actually allocated something, let's say. I would imagine, at least. If you look inside main base, yeah, that's not really obvious where our code has allocated stuff. But if we look at the number of total allocations, we have 4,000,000 float 32s being allocated. Some strings, some ints, a lot of any values, which is interesting as well, but 27,000 of them. And we also have this CodeGlass unknown type. This type is something that CodeGlass cannot figure out what it is, what I would imagine. Okay, let's close that as well. Let's go back to another view. Let's see maybe the code heat map. So this heat map is already giving us more detailed information about what's slow in our code, at least by the number of total calls. This strcmp is string compare, is a C-call thing. We have not touched any string related functions, so this is from probably just from the normal Julia startup. The division between a float 32 and a float 64 is taking a lot of time, and the conversion of a float 64 into a float 32 is taking a long time. So we know that most of the time in our code is spent probably by these two functions. Okay, so I'm back here in the statistics view. I'm going to look inside the normalize function now to try to understand better what's happening in my function. It has been called twice because we have just called it again, right? But they were both called with the same data, so it should still be the same idea. So first of all, this more specific call, this is my normalize function. This is the input as inferred by the compiler. This is the output as inferred by the compiler, has been called twice. Statistics, blah, 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 blah. Cool. This is the tentative body reconstruction. This is trying to give you all the paths that the normalize function took. From experience, this is, I don't know, sometimes it doesn't work at all. Sometimes it gives you really useful information. It's not clear when it works, at least not for me. When it works, it's really nice. You can just browse here. We're going to look into that probably into more details. More functions will have the body reconstruction working. Sometimes it will fail to reconstruct the body. It does say go to the code body statistics to see everything, and that's what we're going to do. This is the code body statistics, and it's a little bit closer to what your software is doing in the background. So you can see that it's not really close to what our software how our software is written at all. But hopefully it should be how our software is understood by the compiler. If you look at all these function calls, they are mostly taking very little time. So greater than 0 means that it's really small, but rounds down to 0. But down here you can see that a few function calls are taking longer than that. The division and the conversion, which we also notice from the code heat map, we saw that these two functions were the heavier ones, so it makes sense that they are what's taking the longest time here. And let's try to investigate those functions soon. Before we do that though, we also have the distribution graph. To be honest, it is a bit complicated and I don't know exactly what to look for here, so I'm going to ignore that. Multiple dispatch, when you have multiple dispatch of this function, they are being shown here. And the dynamic dispatch, which is usually really useful. So from this tab, we can see that, okay, my normalize function has a division, has conversion, and has a bunch of other things that are being dynamically dispatched. So something in our code is not being inferred during compilation time. And that is the main information that we can get from CodeGlass. Something here is not being correctly inferred. If you write in Julia code, you normally want things to be correctly inferred because that usually affects your performance. So you want to look back into your code and try to figure out what is not correctly inferred. So again, we can see from here that the division and the conversion are dynamically dispatched. We saw here that they are taking a long time. So let's look into one or both of these two functions and try to gather more information. So I'm just going to select convert here, double click, and you can see the body reconstruction of this function is completely fine. It doesn't show anything to us, but it's completely fine because here on the right, there is only one path and that path is being correctly identified. It has been called from a normalize function. So here on the left, you can see that the main.normalize function called that, and that function has dynamic dispatch. So the convert itself is not the issue, but dynamically dispatching on convert is the issue. Same for the division. So if you look into the division, you're going to see the same information. The right side is saying this function is fine. It has been called from a function that has dynamic dispatch. So it's possible that you have already figured out why our code is dispatching on the conversion and the division. So if you look back into our code, most of it is clear, at least for me. I think the result is similar to data. Data is being correctly inferred. It's defined here as array 32. The input was correctly identified as an array of float 32. Result equals similar data. We had no issues with the similar function. We did not found it anywhere here. So similar is not even popping up here. So it was possibly in line by the compiler. Not an issue. For I in each index of data, so possible that each index did have, nope, nothing bad happened specifically with each index. Okay, I did have to restart stuff. It's back on the same place as before. I just have called normalize data once, but the analysis is still the same. If you check main, normalize, body reconstruction still failed, dynamic dispatch is still the same place, okay? The normalize function correctly infers that the input is an array float 32. Looking at these bad functions here, we don't see anything indicating that similar has an issue or that the loop itself has an issue. However, we see that dividing has issues with the dynamic dispatch. So if the division is always dynamically dispatched, means that we don't know the type of everything in the division. Data is correctly inferred. Data I should be correctly inferred as well. So the scale is not inferred correctly. And if enough, Julia, to see at least the performance tips page, you know that this is a best practice that we have here. We have defined scaled globally, and scale is not a constant value. So this function has a non-const global, which is not correctly inferred because I could just change scale to be complex value here, and then the division would be a different dispatched division, right? So that's why that division is always being dynamically dispatched. So the solution for this problem is to define a const value. So I'm going to create a const scale. I'm using a different name so we can compare that. And we're going to change the function normalize. But before we do that, I want to show you one last interesting feature. In statistics or anywhere else, actually, you can just click on this button here, which looks like a recording button. And you can start a new recording. And now only what I run at this moment will get recorded. And we can see here in this drop down that only what happens now will show up. So first normalize data. Only that one function call is here. I can stop, start a new recording, and then I'm going to create a new function, which is the same function as before, but I'm using capital scale, and I'm going to call normalize again. So now this new function here, again, source 7, has only one function call, but you can see that the time that it's taking is much smaller, so only 3 milliseconds in comparison to the original one, which was 800. So this is indeed faster, and that was apparently the issue. If you look at the same information as before for this normalized call, refreshing the data, it's still showing dynamic dispatch, but I'm thinking that this is because it wasn't updated. This has happened before. When the function call hasn't been updated and the name is the same, I'm guessing that it has some limitations on knowing what is new and what is not. Yeah, for dynamic dispatch, you don't have that option. You can see here that this color changes. So I can't really see only the specific dispatch for the recording. Just to showcase the difference, I will create a new function, normalize const. So this is the normalize const function, which is the same thing, but with a different name, so that I can see, yes, here. I actually see now that I have a small issue. I'm not sure why exactly, but I have an unstable connection with the engine. So I just closed the application, I stop it, I kill the running thing, I will close this tab, refreshed, now it's back to being green, double click. The first time that I ran this, it ran to completion. I'm going to start a new one, and I'm going to quickly create everything that I had before. Okay, so calling normalize only, calling normalize const after that. And now we can see both functions are here. We had to restart the application, but that worked now. And now we can see that the const version is much faster. And if you look at the body reconstruction, you can see that apparently we still have a dynamic dispatch on whatever this is, a UV finalized timer. Honestly, I don't know what that's supposed to be. And again, honestly, last time I tried this UV finalize did not appear. So it's good that we are seeing that live. I'm gonna leave it like that. I'm not gonna investigate more why that happened. But leave it in the comments if you know why that's an issue. Okay, so I have started a new application to try our new example. Still in the same situation as before. I have Julia open, nothing happened so far. And this new application uses a struct. Okay, so this is our new example. I have created a struct called myStat, essentially keeping some statistics. I have a real value and a count. essentially counting how many data points I have in these accumulate stats, and then summing over all of these statistics values in this stat total. So accumulate stats will just loop over all the data, save the sum of the data, and count as they go. So first of all, let's just call accumulate stats and see what happens. In the meantime, you can already start guessing what is the issue. I'm going to create my stat here. So start with a 0 and then the data. You can see that it's taking some time to run. That is, my code already takes some time, but you should also take into account that you have some overhead for CodeGlass. Depending on what you have enabled, you're going to have more or less overhead. The worst case is 10 times more overhead if you're tracing everything, including some deallocations. By default, that's not turned on, so it's maybe 2 times slower, something like that. What matters is that this is taking a long time. If we change to seconds, you can see that this took, well, it shouldn't take 2000 seconds. Yeah, this is the full main. That's much better. It doesn't take 2000 seconds. I don't know why it's saying 2000 seconds here anyway. But the accumulate stats function, which is what matters, took 11 seconds or 15, with everything that it's calling 15 seconds, right? My stat creation, which was also called here, my stat 00, was quite small. My stat was called 2 times, which if you look into the code, doesn't happen. I only called my stat once, so possibly somewhere here, maybe in the return function, maybe in the creation, my stat was created another time. I wasn't following to see exactly when that happened. That's a pity, but for now that's it. The thing that matters most is that accumulate stats is slow. So why is it slow? Again, if you look at the double click here, if you look at the direct information from accumulate stat is a my stat, the data is this array, and the return type is my stat. This was correctly identified. No body reconstruction, again, possibly because this is hard to reconstruct in this state. So looking at the body statistics, you see again a lot of things happening in the background. I'm not sure exactly when this happens, but I have a guess, and my guess is that when you have some bad dynamic dispatch going on or something like that, all of the internal calls, they also get a little bit hazy, and so everything appears here. The things that really matter are at the end, in this case at the end. Plus, it's taking a long time. Set property twice is taking a long time. Dynamic dispatch, so what is dynamically dispatched? Everything is dynamically dispatched. Similar situation to what we just had with our other example. This case is not a global situation, I just have a struct here. So why are things being dynamically dispatched? So set property is this part here, stat.total equals something that uses a set property. Plus, so this plus, this is stat total equals stat total plus x, so this plus is a dynamic dispatch. So again, it's not being able to correctly infer the type of things when in this loop. Why is that? So again, if you look at the specific things that are happening here, data correctly inferred, stat correctly inferred. X in data, I think that's correctly inferred. It's not exactly obvious that's correctly inferred from our code for the code body statistics or anything like that. But since data is nothing fancy, it's just an array, X in data should be correctly inferred, or at least we expect so. And so the only thing that's possibly odd is the stat.total is having issues, so it's not being correctly inferred. Let's also look at the code heat map. Again, the code heat map shows main issue is the plus and the set property. Those things are really slow for this function call. So one thing that might help you determine what is wrong here is this myStat type actually. So you can see that the myStat type was created normally, everything here is fine. This is no issues, right? However, two things pop up. First of all, the types that were inferred for my type, float 64 and int 64, are not the same type as my struct. So this struct definition implicitly creates a new function called a function myStat, but this function is implicitly created. So myStat function, which is this constructor here, was inferred to have received a float 64 and an int 64. The function to create myStat worked fine, no issues in that function. But it returned a myStat, and the types of myStat are not the same. The type of myStat is a real, and the other type is an integer. These are abstract types, so they catch float 64 and int 64, right? So that's fine. And the other thing is that this function called has dynamically dispatched. So even just the constructor has already dynamically dispatched. So something in this constructor is bad. And so maybe stat has some issue. Body statistics doesn't show anything. So again, if Julia enough, you know the issue here. So the issue is that ideally you want the types of your struct to be concrete. And the types that we have here are abstract. The real type is an abstract type that covers float 64. Float 64 is a concrete type. Concrete types are what the compiler is trying to infer. So having abstract types doesn't help at all. It's not allowing the compiler to specialize. And then every time that you say stat.total, you are essentially figuring out the type of total when you run it, because it could be any real type, right? So I could have my stat dot, and I actually want to see what happens here. I haven't tested this, so I'm going to start a new recording, and I'm going to look only at that one recording. Yeah, we are on main. Maybe I want to open base. Yeah, let's see. So my stat, just by pressing keys, a lot of things pop up. This is a bit annoying, to be honest. I'm gonna close this. I hope that's not where things pop up. So calling my stat with 0, 0. Here, if I say my stat float 32, 0. Yeah, let's do this. It's a different call. So here you can see it's still fine, no issues. This is the other one, fine, no issues. This is from the old call, so I can call this one. Both of these are from the source ID 10, which is the recording, and you can see that they are pretty much the same. One thing that I just noticed, for some reason, this one says that run standard repo contains dynamic dispatch. This one doesn't say that. I don't know why. And the dynamic dispatch on this one is empty. Refresh, doesn't show anything. And this one, it does show the original one. I don't know why. To be honest, that's a bit of a guess. But the most important part is that, and I actually can click to filter the dynamic dispatch ones. We haven't used that. But the important thing is that my stat has been dynamically dispatching, and that is breaking my accumulate stats function. So what we're gonna do now is stop this, start a new recording. Let's just call this accumulate one last time. And let's change my stat to be correctly inferred now. So the solution to make my stat correctly determined is to define it with the correct types. I have created a myStat typed, just so I don't overwrite the same type again. And when I call, I don't have to change the function at all. I just have to call accumulate stats and give it a different type. And by the way, yeah, this was for the old one. Stop, new recording, 0, 0, data. Yeah, let's do that again. And this is the other one. Good, and I can stop both of them. So if we look at the global information on source ID 9, you can see that accumulate stat has two different calls, one with myStat and one with myStat typed. and you can see the difference between them here. So the average call for the first one is 15 seconds and the average call for the second one is 6 milliseconds, which is faster, which is expected to be. So if you check this second call, body reconstruction is fine, no issues. Dynamic dispatch, no issues. Multiple dispatch, doesn't matter. You can see everything went much more smoothly. We can also just check individually the source 11. So source 11 units seconds, turbo 16 seconds, source 12, beautiful, less than 0.0001 second, which is good. Another solution to this problem, because maybe you do want your real type to be, you want to catch. So another solution to this problem is in a situation where you actually need the total to sometimes be a different type than float 64, is to use parametric types. So you could have a mutable struct myStat parametric, and then you have two types, TF and TI, and then total is a TF and count is a TI. If you create a myStat parametric with 0, it works. If you change this to a float 32.0, it also works because it's parametric. And you can see that the type of myStat parametric is this whole thing with the braces indicating which specific type is being used in the parameter. And if you call accumulate stats with myStat parametric, this should, first of all, it was faster, but this should also be around the same speed as myStat of the accumulate with myStat typed. So here, yes, a bit annoying to see without the milliseconds. And let's change longest call. The second one, so the myStat parametric, 8 milliseconds, myStat typed 6 milliseconds. Around the same order of magnitude, which is expected. I'm not gonna try to benchmark to see which one exactly is faster or why. Doesn't really matter. The most important thing here is that they were both correctly inferred. And if you check myStat parametric, same idea as myStat type, no dynamic dispatching. Same for myStat type here. Apparently this was still dynamically dispatched. I'm not sure exactly why this sometimes dynamically dispatches myStat type. And if I check myStat parametric, yeah, sometimes it still dispatches. I don't really know why. Do I know why? I don't, and I won't try to figure out. The most important part here is that the thing that was making it slow is not making it slow anymore. This is once more an example from the performance tips in Julia, so you already know that this is an issue. This is just a way to figure out, to help you figure out where that issue is happening. Okay, so I have a new example. I have just started a new CodeGlass instance, and I have created a random graph function here to create an example of a flow problem. So I have nodes and edges. So the nodes are just one range from 1 to 10,000. Edges are a bunch of pairs of numbers. So you have node 4057 to node 686. So you have an edge, an arrow that goes from that node to the other node. And you have demand, which is just a dictionary per node giving you some information. So this is an example or simulation of a flow problem where some nodes have demand and some nodes have production. I'm calling them all demand, and it's a production, it's a negative value. And the idea is that I want to write a model to do something on top of these, either minimize the total flow that I have to create or where it needs to go through. So each edge has some cost, etc., etc. I'm not going to do any of that. I'm going to do just the simplest version of this, which is I am going to create the flow variables for this, and I'm going to create the balance constraint. So in each one of those nodes, everything that's coming in, so every flow that arrives at the node must be equal to every flow that leaves the node except for the demand. So if I have positive demand, it's going to increase whatever comes in, plus the demand must be what goes out. If it's negative, it's also going to be incoming plus the demand, but since it's negative, it's like it's a production on the other side. So production plus incoming equals outgoing. So essentially it's just balancing everything that's produced minus everything that's consumed, right? Everything that I get must be equal to everything that I use. Okay, that makes sense, right? So for this example, we are modeling an optimization problem. We are using jump. If you already know jump enough, you may have guessed which issue I'm gonna show. If you haven't, you're gonna have a really good chance to figure out what the problem is with the code that I'm gonna write now. Okay, this is our function. This is our model that we are creating with jump. You can see that it doesn't have any objective, it's just the variable and the constraints, simplified model. But from this, you can already see the issue, right? So let's just build this model. So when we call build model, nodes, edges, and demand. Oh yeah, before we do that, you can see that just installing jump and etc. already did a lot. So I'm gonna start recording and look only at the recordings, so it's gonna be easier to follow. Okay, running that. It's over already, so I have a few function calls. Let's see, of course we had main, but we also have ccall, jump, matop interface, order collections, mutable arithmetics. These are all in the background of jump. What we care about is our main function, and from here we had two function calls. We actually only define build model, but we have this hashtag build model, hashtag number 2, and this is an anonymous function or some kind of function that was created internally temporarily. It's inside build model, so that's why we have this build model name here, and it's not immediately obvious where this function is, what function is that, and that is a little bit related to the issue, as we'll see. Maybe you can see that immediately because the build model time is exclusively is just almost nothing, so the function itself is not doing anything fancy, but the inclusive call, the things that when you call this function, the things that it calls are taking 1.5 seconds, right? And if you look at the build model number 2, which we guess was called by that function, it was called 10,000 times. The time that it took on itself was almost exactly the inclusive time, so it means that this function is taking a long time, especially because it's been called 10,000 times. The average call is really small, but since we're calling it 10,000 times, it takes a long time. Okay, let's start our investigation by just going into the build model function, seeing what happened here. So we are going to look into this body reconstruction with a bit of patience. So build model itself looks fine, took 0 seconds. Jump number 1, whatever this function does, it was fast enough. So this clock function is not in our code. We don't know where it comes from, so probably internal to jump. Jump.error if cannot register, so this again internal to jump. This container thing, so containers.container, and then inside you have a function that is a build model function number 0, so it's not our number 1 function. And you also have this number, so hashtag 0, hashtag build model, hashtag 1. Really no idea what exactly this is, but this was called by jump, took 179 milliseconds, maybe something here. Continuing, whatever this dense axis array is, it's not taking too long. If you jump enough, you know that this is the output of either the add variable or the add constraint, because it's a dense thing, it's linearized. So jump generic variable ref, So this is probably the output of the at variable, which is this call here. Some set index, then this has a else. So here, if param, something happens, else something else. Not exactly sure why this if else happens, but it happens, at least here on the body construction. The container on the second branch takes longer and is the container that calls the build model number 2. And there is also a build model number 3 here. Why do we have build model 2 and a build model 3 together written like this? Not sure. But the interesting thing is that this is where the problem lies. It's where the most time was taken, so from the profiling point of view, this is the slow part of the code. That's where we're going to investigate. If you check the body statistics, this is going to be the same information. This container call is taking 1 second and this one is much less. Dynamic dispatch on this, we have the container for the two things. One of them dispatches on everything, the other one dispatches on everything. So as I mentioned, Jump has a lot of dynamic dispatches, so maybe this is not an issue. Okay, I'm gonna close this and close this. So let's try to investigate where this issue is coming from by analyzing this function call. So I'm back here on this containers.container. Again, I'm guessing that this containers.container comes from one of these at variable or at constraint macros. Because they are macros, they are converting that code into something else, which I guess is this containers.container. So let's look into that. Body reconstruction did not work. We can check the dynamic dispatches. It's what we just saw in the other tab. Body statistics show more interesting things. So since the body reconstruction did not help us identify the problem, we go to the body statistics. The first one, collect, has all of the time. So let's go into collect, double click. Loading, collect still has some issue reconstructing the body. So let's check the statistics, finding the issue again. And you can see that build model, the first call build model takes 27 seconds, one call only. Going down more all the way, we found out that in the end we have a collect to with first that takes almost all of the time, so that seems to be more important. Let's double click on that. And this one, by the way, the body reconstruction worked, and you can see that it's only one thing here, which is collect to. So when the body reconstruction works, things work much better. It's much easier to navigate this. And as I mentioned in the other exploration, sometimes the body reconstruction works, sometimes it doesn't, even with the same function call. So if I close this, start over and write the same function, sometimes it works. So sometimes just resetting and trying again, maybe that's enough. But anyway, so here the body reconstruction of collect to, things start to get interesting because now we have a for loop. So 9,999, which I'll just say 10,000 times, is the number of nodes. So something in the order of the number of nodes is calling this second function build model number 2. In the future, you could skip this investigation and just jump directly here. So if you double click on this model 2, or if you go back here and you double click on this model number 2, you go to the same place and you find this build model number 2. It failed to reconstruct the body, but is our latest guess of where the issue is. Okay, now from this we want to try to identify what is the issue with our code. And the thing is, I'm doing this with you because when I first did this on my trial run, the body reconstruction actually worked completely, and so it was more like this one, where I could see a bit more information, for instance, about this loop here that made this call slow. And here I don't have that information, so this is going to be a little bit more interesting because we are essentially learning together. So to be honest, we are having a little bit of a trouble identifying exactly where the issue is coming from. One thing that I will try before I just jump to the solution is I will create another recording. So I'm gonna stop this, start a new recording, and I will try to just call that build function again. Okay, so now that I have started a new execution, new recording, I ran again build model. The body reconstruction now worked. It worked in an odd way where I have 28 out of 22. It's saying the completion rate, it's over 100%, so I'm not sure what that means. But this gives us a little bit more information, which is what I was looking for. And this information here is what I would say it helped me figure out, okay, this issue is related to something in the order of 2 times the number of edges. The 19,000 times was already a strong indication that something was happening on my function here, but in particular in each one of the summations, because I had for each node, the sum happens twice. So the sum has something there going on, and you can see that the build model has this part here has been called 199,000 times, which is the order of the edges times 2, right? So if you remember the order of the edges, huh, 199,902, which is exactly the number of times that this was called. So it looks like I am doing something that allocates a variable for me for each one of these nodes, for each one of these edges, twice, let's say. You have to pre-compute this filtering here. So when you do a filtering inside a macro, that's usually a bad idea. So if you have a conditional in there, beware. It rhymed, but it's by chance. So yeah, you can see here, so after that you can see that in this first branch, if param, I don't know what that means, but 5 calls, 10,000, 10,000, 10,000, 10,000, 10,000, 10,000, something here that's around 10,000. Else, 159,913, which is the number that we saw for add or set. So this we had before. Why is it 159? I don't know. I still don't know. If you do know, please let me know. Write in the comments. Anything. It's interesting that this number specifically has appeared. But after that, we have another time, once more, 199,902, which is the base get index. Inside the base get index here, we have this 199,000 times. Last time we checked this together, it was, let me just double click here. Yeah, we had this number, 149,000, but we also have plus 20, plus 10, and maybe that's why, is it? Yeah. I don't know why. Let me know. I don't know, but it is oddly, it was split into 4 call sites. I don't know. These macros are hard. That's what I would say. Profiling is also hard. Profiling macros expectedly hard. So that's that's an issue, but that's fine. We are learning how to use this. The important part is that we figure out that from the number of times that this is executing, this way of building the model is not great. So let's build a model slightly different. So this is our new function that shouldn't have the same issue. Instead of filtering the incoming and outgoing edges inside the macro, we compute the in nodes and out nodes, which are essentially just looping once over the edges and creating these arrays of integers with the incoming and outgoing, the corresponding edges of the incoming and outgoing, so the corresponding nodes of the edges that are incoming and outgoing. Yeah, that's a mouthful. but that's how you do it. You just filter those things beforehand, and then when you go loop over them, you just say sum the flows for j in nodes. So this doesn't have a conditional. This gets optimized by jump. That's the trick. This part gets optimized. This one doesn't get optimized. That's it. For what we care about, we are going to build the model once more. I will not stop, but I will change the recording. Stop this recording, create a new recording, and then build the model again. I probably made a mistake. Close. I made another mistake. Yeah, I had I and j swapped. That's it. Okay, so I just ran this again for one recording that I did not make mistake. Here's the build node. So if you check build node only called once, build model 2 is still being called 10,000 times. The time that is being taken though, it's faster. So here is 497 milliseconds, and the original one, which is for source 14, was 3 times that amount, so it's much faster. So to make things simpler to investigate after the fact, I have created 2 separate function calls, the build model slow and build model fast. And you can see here that build model slow takes around 1 and a bit seconds, and build model fast takes a bit less than half a second, so indeed they are faster. If you investigate their internal function calls, that's build model fast, which is again the main culprit in this long time, right? So the inclusive call here, you can see that is almost the same as the higher level call. If you look into a bit of details here, you see that the number of calls is still the same. They are still being called 199,000 times, but they are much faster, each one of them. And why are each one of them much faster? We still have a summation that goes over all of these in nodes, and these in nodes will be all of the incoming edges, and the out nodes will be all of the outgoing edges. That means that all of the edges will be accounted, so around 2 times the number of edges, which means they are still the same. However, each time that I go over one of these edges, I don't have to do a filtering of all the edges. So the filtering step is faster. We don't have to do that, and that's why this whole thing is much faster. So the main question here, and this is still an open question, maybe I'll come back with a new video explaining all the details. How could I figure out exactly that the issue was on the filtering of the function, right? Of course, I know it's the filtering, so maybe I could search for the filtering specifically, but just looking at the code in details, could I have figured that out? Could I have found out that the issue in the first one was the filtering, and the second one, even though it's pretty much exactly the same, it's just faster because it has no filtering? I don't know. Let me know in the comments. Thanks a lot for watching this video. I hope you enjoyed learning more about CodeGlass. It is a complicated tool, of course, because we are dealing with profiling and tracing information, so a lot of things happening. But it's a new tool for Julia that's being actively developed, so we hope that it gets all of those ragged edges smoothed and made easier to use for us Julia folk. If you want to learn more about how to use CodeGlass, let me know in the comments. Please ask for specific examples of what you're looking for. I can look into how that would work for you. And if you're also interested in how could I investigate this without CodeGlass, how could I find these issues without CodeGlass using the traditional Julia tooling, let me know as well. Please leave a comment saying what you have tried or what you would like to see being done, and I can try to create a video about that. Thanks a lot for watching. Please subscribe if you enjoyed it, and I'll see you in the next one. Bye bye.